Good morning, everyone. Hi, I want to welcome you to another statistical learning class. And of course, today, the focus is going to be on miscellaneous topics in linear algebra. But I think since this class does not involve lab section, and I know that the use of R is very crucial to this class. Uh, from now on, I'm actually going to be also showing you some useful R codes. I've updated this material. You can check the canvas. I just posted it now. This material. I include some R codes, and not only that, uh, I'm going to give you some useful tips on homework one. So before I go into the miscellaneous topics in linear algebra, I'm actually for us show you some clue on, by giving you some hard codes, in case you want to navigate your path solving that assignment. So let me go straight to the business. Now, I'm going to use data set that is well known by researcher Harris data. Okay. No, the areas that actually look like this, this is just the first six of the average data, there are so many. Okay, you got some variables. How is data qualified to be multivariate data? Because I'm actually seeing something arranged in row and column. The number of observation is in row. The number of columns. The column is actually representing features, the variables here. And of course, the response variable also included the one I call outcome variable species, this looking to me like a classification problem. Of course, this is supervised learning because in addition to having explanatory variables, of course, you have the outcome variable. Now, the article I just want to show you today is if you have a multivariate data set and they wanted to figure out, or maybe they wanted to generate a plot, or they wanted to compute some basic statistical stuff. Now, I needed to pay attention to this if I want to generate a scatter plot. The moment I have the name of my data set saved in R, I just need to write PS, PS, PAIRS. Okay, in the parentheses, you can decide to put the name of the data set. And of course, what you're going to see is what is being displayed. Now, what is being displayed right now, okay, what I'm only seeing the scatter plots, different scatter plot, you know, because there's something I want you to observe, okay, and when you look at the diagonal, okay, when you look at, give me 1 second, I'm actually gonna write something now. When you take a look at this guy, what I have here is the same as what I have here. They're gonna be the same. Okay, they're going to be the same. So if they're going to be the same, what I can do, I can just tell R to give me that. You see the code, I'm going to show you the code. I'm indicating I'm only interested in the upper. Okay, and that was why you see lower dot panel equal to no. I'm not interested in the lower one because they're going to give the same. Take a look at that. So this is generating scatter plot matrix. Okay, just wanted to take note of that. Okay, so if I want to make it more beautiful. Okay, if you take a look at what I have right now, okay, if I want it to have colors, okay, why do I want it to have colors? Okay, because if I want to distinguish one from the other, okay, I'm not just going to write that code. Take a look at the code that I'm writing now, okay, and I'm going to have that. Take a look at that. I've indicated, there's a color now. You see the color? Now, the color represent what? Oh, the color here probably, is representing, don't forget, we have a label. We have a variable supervising here, species. Okay. We got different kind of species. So that is the idea of bringing in the color. Okay. Not only that, I can do a lot of stuff. Okay. Um, you know, uh, moving away from that, uh, what of in a situation where I want to add correlation value because I'm only seeing shape, okay, I want to add correlation value, okay, this is the code, to do that. All what I need from you is just to manipulate this to suit your whatever data set they're going to give you. Okay, take a look at what I have right now. I already have, correlation value, incorporated into the structure. Okay. Now, there's so many ways I can incorporate correlation of value into the structure. Another way, take a look at this. What are you seeing now? On the structure, you can see the value of the correlation each. You need the values of correlation in case of those who may not know how to read the graph. Okay, take a look at that. Okay, I just needed to take note of that. I want to believe that with this, that assignment is a walkover. That assignment should be a walkover for you. Now I can decide to go all the way, or what if in a situation where in addition to you know, generating the scatter plot, I also want to, uh, impose, or maybe I want to incorporate another kind of plot. Okay. But if I want to do that, I would need to load a package inside out. So if I want to load a package inside out, PSYCH, okay, maybe I want to indicate, I want to incorporate a density plot in addition to the scatter plot, or I want to put a histogram, and I want to put some other things. If I write that code, I'm actually going to get this. If you take a look at what I'm displaying now, okay, I have scatter plot in this. I have a correlation, and at the same time, I can see an histogram all imposed in a, in the image. Okay, I believe this will now give you clue. You need a software for multivariate analysis. Without software, you can't do multivariate analysis. And of course, for those of you who have attended my course, the course that I taught before exam, I normally release practice questions, and of course, I walk a student through. I dedicate a class for revision, where I walk the student through the practice questions, and of course, the practice questions normally closely match the questions in the exam. So all what I need from you is attend my class regularly, pay attention, watch my videos. If you put my name, I've published all my recordings on YouTube. If you put my name on YouTube, you're actually going to see the video, but make sure it is the video for your class. When I post video now, I put the class, like for this class, staff 5401. Okay, so make sure it's for your class. Okay, so this is the step. You know, Another way to go about it. Let's say I have data set and you import data set into R. You have to attach the data set, and if you want to or have the sense of what are the variables in the data set. Then you can write names into whatever. Now, um, if I want to do scatter plot again, okay, you can actually load some, packages. Okay. Now, at times, let me tell you this. There are so many variables in your data frame, but you are not interested in all of them. I'm going to say that again. You got so many features in your data frame, but you are maybe the question, they ask you, it is not about all of them. Maybe in the features I'm interested in is A, B, C, D, not all. Then this is a code in R. Okay, this is a code in R. If the entire data set is called data, I'm just assuming here, okay, how then I actually want to have a subset. I want to select those variables the question is based on. Okay, maybe based on ABCD. Okay, that is the subset. I'm going to give it a new name right now. So a new name. Okay, I'm going to extract the variables that I'm interested in. And after that, if I want to create a scatter plot, it's going to be on that particular variable on, I mean, the new data frame that I just created. Okay. Now, after that, now some of you have been asking me, how am I going to get a mean vector? How am I going to get a covariance? If you want to, the moment you have your data set, now, right now, subset, okay, is the name of my data set. That subset represent the variables that I extracted from the original data set. Okay, and of course, here is trying to say, okay, there's possibility you could have some missing values, okay, in the data set. If there's missing value, okay, that's going to take care of that. Then the moment, and you can say column means, the column means, I mean, we actually want to get the mean of each variable, okay. Then the next, you can go for variance, covariance matrix. That is how to do that. Take a look at that. Okay, and you can also do correlation matrix too. Okay, take a look at that. Okay, so I will advise that you trying to study run the article that I'm actually going to be putting in lectures, okay, for better understanding. I'm not going to deceive you. Uh, you know, um, you need the knowledge of a software, how to be able to succeed excellently in this particular course. Now, this particular course is not going to be highly theoretical, but it's going to be practically based. Practically based, where the interest, where the emphasis is going to be on analyzing motivated data. Does that make sense? And that is why it is called applied multivariate analysis. I want to go into today's topic, miscellaneous topics in linear algebra. Okay. Um, we want to talk about quadratic forms. Okay. Because in motivated analysis, okay, quadratic form play crucial role. If you are working on problem optimization, okay, where you needed you want to minimize a function, and you needed your function to be not to be concave, to be convex, okay, so that because you want your optimization to attain what I call global maximum, not global minimum, global global minimum, not local minimum. Okay, I'm gonna say that again. You're seeking a global minimum, not local minimum. Okay, the idea of a quadratic forms is necessary. But what we're doing now is just for us to walk you through the mathematics around that. We have a way to figure all of this out using the software. But we can't go directly to software like that. You need to first understand what is programmed in the software. The software can't do anything without any formula being programmed. Okay. And that's why what I'm trying to walk you through, what we're trying to walk you through is for us, for you to be able to understand what formula, what technique, this, that. If I have a symmetric matrix A, we all know what I mean by symmetric matrix. And of course, I actually have X matrix, a vector, and there's another one at this side. And I use them to multiply the matrix that I'm talking about. Okay, then we can actually investigate this quadratic form. We can investigate what we got for, it could be greater than zero. Okay, it could be greater than zero. If it is greater than zero, we call that positive definite. Positive definite as our application in multivariate analysis. Okay, it could be greater than zero. It could be greater or equal to zero. If it is greater or equal to zero, we're actually going to call that positive semi-definite. It could be less than zero. That is called negative definite. If it is less or equal to zero, then negative semi-definite. Okay, now you know, in multivariate analysis, of course, particularly when you are using what I call you know, the derivative approach, when you're using a second order derivative approach, to decide on optimization. Okay, you are optimizing, maybe you are minimizing. We normally want to investigate the quadratic form. Okay, and what we're trying to tell you here, okay, for you to be able to investigate the quadratic form, okay, then you need to multiply three things: S transpose A X, and whatever you get can be investigated. Okay, and that's exactly what you see. Okay, now this is just a mathematics example. Okay, this course is not just going to be 100% applied, because you cannot do applied without having a theoretical foundation. Okay, but I'm gonna do, I'm actually gonna make theory to be 30% and apply to be 70%. Does that make sense? Now, when you take a look at what I have here, if I have a matrix A, okay, I want to investigate whether this matrix is positive definite or negative definite or semi-positive definite or semi-negative definite. Then I need to investigate, I need to obtain the quadratic form. Now, if I want to the quadratic form, take a look at this. How do I know? I'm actually going to use x1 and x2. I'm going to use x1 and x2. I'm going to use two variables because this matrix is 2 by 2. If it is 3 by 3, three variables. 4 by 4, four variables. Does that make sense to everyone? Okay, now I'm going to perform that. At the end of the day, I got this expression. Please pay attention. Pay attention. Take a look at that. I want to investigate this. I want to see whether it's going to be greater than zero or less than zero. The only thing I can do, if you take a look at that, because x1 squared is going to be positive, x2 squared is going to be positive, and x1 minus x2 all squared also positive. Okay, because of that, I'm actually going to say that guy is greater or equal to zero. Does that make sense? It could be zero or greater. It can be negative because of the square. Now, because I got greater or equal to zero, I'm actually going to conclude here that this is semi-positive definite. Does that make sense? Okay. Now, now, this have implication in principal component analysis that we're going to start. As a researcher that is uh maybe you are presenting your research work, and you are not in statistics, but you've used statistical method. It is expected that you have an average knowledge of, of the method that you are applying, and that is why we're working you through all this. Now, if lambda j denote the jth eigenvalue of A, okay, now, some useful property of the matrix definiteness. If A is positive, let me tell you something. When A is positive definite or negative definite, it has an implication on eigenvalue. Okay, like I said here, if A is positive definite, then lambda j is greater than zero. Because don't forget the lambda j in principal component analysis represent variance, and we expect the variance of a feature not to be zero. At least variance have to be positive. Variance can be negative, variance can be zero. Then we need a strict positive definite when it comes to variance. Okay, now if A is positive semi-definite, then lambda j greater or equal to zero, which means we say, okay, maybe variance can be zero or positive. Okay, but situation where A is negative definite, lambda j less than zero, of course, if you are talking about variance, that is not going to work. Does that make sense? Okay, that's what I mean. Okay, I'm going to move. I want to go into something else. Matrix determinants. Let me tell you this. When you are working, maybe for next week, okay, uh, when we're dealing with multivariate linear regression or something, okay, let's say for instance, I actually want to look at effects of age. I want to look at the effect of age and gender, okay, on blood pressure, okay, on blood pressure. Let me do this. Okay, on blood pressure, okay, this is my outcome variable. This is X1, okay, and this is X2. Okay, so I'm actually going to use uh, a multiple linear regression model. Okay, that is my model in matrix. If you take a look at what I have here now, this is in matrix form. Y is in matrix form. Okay, Y1, Y2 until I get a YN. This is in matrix form. This is also in matrix form. This guy is also going to be in matrix form. Okay, that guy is also going to be in matrix form. If I want to write this one is scalar, what I mean, beta naught, beta 1 x1, beta 2 x2 plus the error in a scalar form. Now, if I want to estimate, so the focus is to estimate the beta naught, the beta 1, and the beta 2. Okay, if I want to estimate this, okay, the solution to this equation, okay, is S transpose X inverse S transpose Y. Okay, this is actually gonna give me, okay, the solution. Okay, now if you take a look at this, what am I driving at? The inverse of a matrix. If the inverse of a matrix does not exist, there's no moving forward. Now, and why, what could lead to a situation where the inverse of a matrix does not exist? Okay, that depends on the determinant. When the determinant of S transpose S equal to zero, which means the determinant is going to be singular. When the determinant equal to zero, inverse does not exist. Now, and that's why we're talking about the determinant right now. Okay, so you can see all these have relevance in statistical analysis, in multivariate analysis. So what do we mean by our determinant? Okay, this is a notation. If I have a square matrix, I have a square matrix A. Okay, we can write that notation as a determinant, or we can say that A, determinant of A. Okay, and this is what I projected the other time, AS equal to B, AS equal to B. Okay, now if I want to solve a system of linear equation, or I want to estimate parameters in a linear regression, okay, that is only possible if the determinant of a matrix A is not equal to 0. So the determinant now, by determinant, we need the magnitude of that. Okay, I'm going to show you some example, mathematical example. If I have a 2 by 2, or let me just start with 1 by 1. Let me start with 1 by 1. Determinant of A is A. Okay, but if I go to matrix, take a look at this guy now. Determinant of 2 by 2 is just multiply elements in the diagonal. If you take a look at, okay, let me show here. Multiply by that, multiply that by that, then subtract. You see that? Super easy, right? For 2 by 2. Okay, element in the right diagonal, multiply them. Element in the left diagonal, multiply them, then they subtract. That will give you the determinant for 2 by 2. But determinant become crazy when the matrix dimension is increasing. For 3 by 3, we can find the determinant of 3 by 3. But let me tell you this. We have a software, okay, that we can use to solve the determinant. But what I just wanted to know, just you to understand, the mathematics behind, the software. Okay, now you know our intention about determinant. You know, if determinant does not exist, there's no way we actually going to have the parameters in linear regression estimated and so on like that. We'll not be able to get inverse, and the moment we're not able to get inverse, no moving forward. This is a generalization. If I have P by P, okay, matrix, take a look at that, and I can find the determinant for that. Determinant is very, very useful in principal component analysis. Okay. If you look at the mathematics behind getting eigenvector, eigenvalue, and so on like that, they solve characteristic equation. They use the idea of they take the determinant of something. So determinant must, if determinant exists, okay, of course, it's going to, uh, you know, uh, the others are actually going to exist as well. Now, these are the properties of determinants. Okay, if I have a matrix A and I have the transpose of that matrix, if I found the determinant of A and the determinant of the transpose, they will be the same. Does that make sense? If I find the inverse of a matrix A and I find the determinant, it is the same as what you are actually seeing here. And if I have two matrices, if I multiply A by B and I find the determinant, it's the same thing as the product of the determinant for each. This can be proved. All of this can be proved. I just wanted to take note of all of that. Okay. And if I multiply a constant by a matrix A and I take the determinant, okay, it's going to be equal to that. And of course, if A is symmetric, of course, if you take a look at this, the product of lambda, okay, that is not, when you say pi j start from 1 to p, lambda j is trying to tell you lambda 1 times lambda 2 times lambda 3 and so on like that. The product of lambda also the same as a determinant of a matrix A. Okay, and where lambda j in this case represent the eigenvalue. Okay, now inverses. No determinant, no inverses. Okay, so if a matrix as a determinant that is not singular. Not singular means determinant is not equal to 0. Okay, if a matrix has a determinant that is not singular, the inverse exists. It means that matrix is invertible. Invertibility depends on non-singularity of the determinant. I just wanted to take note of that. That's exactly what I'm trying to say. So a square matrix, not necessarily symmetric, is invertible or not singular. Okay? If there exists another matrix B such that AB equal to that. Now, what happens is if I multiply A by B and that give me identity, IN is identity of n dimension. Okay? So that's just a rule. Then I'm going to say if B exists, because take a look at this. That very B, if I multiply A by its inverse, I'm expecting identity. Okay, so this guy now is acting is the B they're talking about, which is identity. So the moment I have this, then I'm actually going to say this is the inverse of A. That's what we mean. That is the inverse of A. Okay, an example here. Let me tell you this. The most simplest subject on the whole universe is mathematics. I'm going to say that again. Is the most simplest subject, But the issue I'm going to tell you the issue we have with maths. We don't pay attention to what is behind every notation, every equation. That is why we got issue with math. Math is sweet. Okay, if I have a 2 by 2 matrix and I want to find I want to find the inverse. Okay, of course, the inverse of a matrix is adjoint of the matrix divided by the determinant. Now, if you take a look at this guy here, that is the determinant, right? The determinant, the reason why, if the determinant of a matrix equal to 0, inverse is not going to exist, is because the determinant is going to occupy the bottom, the denominator, okay, of that. So if the denominator equal to 0 in mathematics, that's undefined. That's what I'm saying. That's undefined. Okay. So I just wanted to take note of that. And of course, this is a proof. Okay. If I really want to know if I have a matrix A, okay, this is a matrix A, and I was able to prove this is the inverse. This is what I got as the inverse. The way to prove whether that guy is an inverse of A is to multiply it with the guy. If you give me identity, I'm actually going to start celebrating. And that's exactly what I'm doing now. So take a look at this guy. This guy is actually the inverse. I use it to multiply A, and at the end of the day, that give me identity. That's a proof. That's how to validate. That's how to verify, or the inverse that you got, whether it's correct, it's wrong, it's correct or not. Okay, so I got so many examples that I'm displaying right now. So you have an A, you find the inverse of A. How am I going to show that is truly the inverse? Multiplying the inverse with the matrix, does it give identity? If it give identity, you're actually going to be fine. Whether you multiply the original matrix by its inverse or you multiply inverse by its original matrix, it will give you identity. Okay, properties of inverses. You can internalize that. So the properties of inverses. Without wasting my time, I'm going to go into, I think I gave a lot of, this is the reason why I say you shouldn't worry about anything, because what what I have in display now is just arrow code. But don't go to arrow code first. You need to first understand. Let me tell you this. If in the world we only rely on software, the world is not going to move forward. Because what is programmed in the software is what just exists to a particular time point, because the what happened in the world is dynamic. Things are changing. We don't want a situation, and that is the reason why we're going to continue to have research. We're going to when we conduct research, we discover something, then we're going to update. We need updating. And how can you update? You can only update where by reparameterizing or remodifying existing structure. But if you don't understand the maths, there's no way you're actually going to remodify. We want a situation. Like I said the other time, we want to model reality. We want to depict reality using a model. But let me tell you this: we actually need to use a model that commiserates with reality. The state of model and the state of reality must match. Situation where your model, where your model does, the state of your model does not match reality. And don't forget, reality keep on changing. The world that I woke up to in some years back is different from the world we're in right now. And that is the reason, before you model, before you specify your model, try to look at the state of reality and the state of your model. If the state of model and the state of reality they don't match, your model is never going to do a great job. Okay, these are useful articles, but these articles, the computer programmer, okay, cannot achieve this on his own. The computer programmer will need to meet with the statistician or with the mathematician to look at their method. That is what is going to program. That is what is programming. So if we want to change, why you need to understand the maths? Because that is, if you want to contribute to knowledge, you want to change, maybe because things are changing. Okay, we don't want to use a static model for dynamic situation. It's going to be an exercise in futility. Okay, now take a look at this now. Let's go to R. Want to use R now. Now, we want to use R for matrix function. Of course, the relevant input of matrix function will include your typical data. You're actually going to have a row. You're going to have a column, right? In your typical data set. Now, take a look at that. From raw data set, I can generate matrix in R. Take a look at that. X 1 to 9, I can tell R, okay, software, you have a job to do for me now. What I want you to do, generate a matrix of 3 by 3. Your software is ready to do that. Okay, that was why you see my data is X 1 to 9, number of row 3, number of column 3, automatically is going to be generated. Okay, take a look at that. That's what I have here. It's generating now. It's generating matrix now. Okay, now, so it's the same code. Another thing you want to do, if you take a look at this, there's going to be some warning. Okay, arrow is very sensitive. Okay, and make sure you pay attention to warning. Okay, now if you take a look at, I have 1 to 9, but I'm asking my R to generate 3 rows and 4 columns. That may not be possible. Okay, so whenever there's going to be an arrow, R is going to tell you. Now, you know, if you take a look at stuff like this, I need you to pay attention to notations, okay, that we use if in coding. Our belief here is that before coming to this class, you've done some extensive work on R, and we advise that you're actually going to build on that. Okay. Now, I want to do matrix multiplication in R. Okay. I specify two variables, my data set, X. I want to use that to make a matrix, and Y. I want to use that to make a matrix. Okay. Okay. So X is 3 by 3, Y is 3 by 3. This is just trying to make, matrix of 3 by 3 for both X and Y. Because what do we want to do? We just want to have some kind of manipulations. Maybe want to perform matrix algebra in R. If I want to multiply two matrices, instead of you to take a pen on paper and start doing all of that, that will waste your time. Okay? Then we actually going to use that notation, or you use that notation, it's going to give you results in less than 1 second. Does that make sense? Okay. Now, and pay attention whenever error message. At times, when you want to multiply matrices, okay, we got assumption. At times, the product may not be conformable. Okay, you actually going to see an error display. Pay attention. Okay. Now, there's another one. Now, obtaining the transpose. You remember in this class, uh, earlier, I actually talked about the transpose of a matrix. Of course, you can also achieve that in R. So if you take a look at this now, I got in my data set 1, 2, 3, 4, 5, 6. That's what I mean by 1 to 6. And I'm asking now to generate a 2 by 3 matrix, which is this guy here, right? Then the transpose is just going to be T, lower T. R is sensitive. Don't use an upper T. T into that. And of course, what you see here, this is a transpose. It's kind of easy. That is a transpose. Okay. Then the dimension, at times, you have multivariate data set, and you really want to know the dimension of the data set. What I mean by dimension of the data set, you want to know the numbers of rows, maybe the numbers of observations. Okay, you also want to know the numbers of features. Okay, in now it's dim. You call that dim? Dim. Take a look at that. Dim is dimension, DIM. Then the first number you're going to see will be the numbers of row. The second number you're going to see will be the number of column. Okay, and of course, where you do transposing, that's instead of 2 by 3, it's going to be 3 by 2 in dimension. Okay, now cross products. Okay, take a look at that. So I put a lot of code here, or what I just need from you. Take your time, study them. Okay, see that row means, column means in the assignment. You can see I gave you stuff like that. Look at that. They are all here. Column means, that means, okay, the diagonal function, okay, take a look at all of that. Then, we did matrix decomposition on Wednesday, like eigenvalue decomposition, Koleski, singular value, and so on like that. Okay, we're not going to ask you to, to compute that manually. No, we're not going to ask you to do that. You should be ready for software, to use software, to be able to do that. Take a look at this. Okay, That one is talking about the eigenvalue decomposition now. Okay. I have X 1 to 9 and the dimension 3 by 3 a square matrix. Okay. And X a cross product X. Then I want to get the eigenvalue. That's why I say eigen. Look at that. Okay. Now, if the dimension of if the mass is 3 by 3, 3 by 3, 3 by 3 actually means I'm only focusing on three features. Okay. Then the numbers of eigenvalues is going to be 3. Okay. That's why you say 3. You see 3 eigenvalues. You see that? You see 3 eigenvalues. You see that? And each of that represent the variance of each variable. Then from there, we go to eigenvector. The eigenvectors is just to know the weight. Okay. Because uh, in principal component analysis, um, the principal component that we're going to form is still going to be a linear combination of the old ones. No, by the time we get to principal component analysis, you actually get to. There is a Koleski, very easy. That is Koleski. Okay. This is a singular value decomposition. We talked about the splitting of matrices the other time, how it works. But one thing is for you, how are you going to know? You can only know what to do using the software if you have some kind of understanding of the theory. Okay? And this is a QR decomposition. So from time to time, I'm going to be including how to code in my lectures. This is where I'm going to stop today. Is there any question for me before you go? Now, before you go, I'm going to say something. Believe that you can have it in this class. Everything in life starts with belief. I just wanted to know that. If you get stuck, reach out. And that's why I appreciate those who visited during my office hour yesterday. My office hour is conducted on Zoom. You can be anywhere in the world to attend my office hour. So let me know if you get stuck. I want everyone in this class to have A's, and that is possible. Make sure you stay safe and have a lovely day. Bye for now, everyone.